Alright, hello guys, my name is Lazaro and today we're going to be doing an easy LeetCode problem. This problem is called lowest common ancestor of a binary search tree. Given a binary search tree, find the lowest common ancestor of two given nodes in the binary search tree. Now, the definition of a lowest common ancestor is as follows. The lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So here T represents the whole tree, but it says that the lowest node in T, so the lowest node in the tree that has both P and Q as descendants. What they mean by descendants is basically this node has P and Q as its child, or its grandchild, or its great-great-grandchild. So for example, let's look at this first one right here. P is equal to 2, and then Q is equal to 8. 6 is the lowest common ancestor because 6 has both 2 and 8 as one of its descendants. And you can't get any lower than 6. Because if you were to go one lower than 6, for example, if you were at 2, you would have P, you would have 2, but you wouldn't have 8. Because every descendant, the descendants of 2 would be 0, 4, 3, and 5, which does not include 8. Now let's look at the second example. P is 2, and then Q is 4. 6 has both P and Q on its left subtree, but we can actually go one deeper. If we go one deeper, now we're currently on node 2. Node 2 would have P, because this current node we're at is equal to P. And the child of 2, one of its child, is 4, which is Q. So that means that this node 2 is the lowest common ancestor between P and Q. So now that we read the description and looked at examples, let's actually get into the logic of this and see how we can solve it. So right here I have the first example, 2 and 8. Now something I want to point out is if you have both P and Q, if P is on the left subtree of the current node we're on, and Q is on the right subtree of the current node we're on, then the current node we're on is the lowest we can go. Because if we go any lower, we would be missing either P or Q. But let's say Q was, for example, let's say Q was 3. If P and Q are either both on the left subtree or both on the right subtree, then we can go deeper. We can go as deep until we find a node where its left includes P or Q and its right includes P or Q. So where P and Q are split between one node. So let's actually work through this example, P and Q. Here, we know, since this is a binary search tree, that means that every node that's less than 6 will be on this left, and every node greater than 6 will be on the right. But how do we know whether we should go left or right? Well, before I answer that, let me just say it's easy to know if P is on the left and Q is on the right, or Q is on the left and P is on the right. Because all we have to do is, we will have to take P. If P is less than 6, which it is, that means P is on the left. And then we take Q. If Q is on the right, which it is not, because Q is less than 6, but if Q was, for example, if Q was 8, then it would be greater than 6. And we know it will be on the right hand side because 8 is greater than 6. And this is how we can determine if they're split. And like we said, once we know they're split, we should just return the current node we're on. But if that's not the case, if it is not split, how do we know whether we should go left or right? Well, to go to the left, what we have to do is take the maximum between P and Q. So let's get the larger number between P and Q. And if that larger number is less than the current number we're on, then we know we have to go to the left. Because if the largest number between P and Q is less than 6, then we know both P and Q will be on the left-hand side. And that's how we go to the left. If we wanted to go to the right, which for this example, it's not required because we do have to travel in the left subtree, but to determine whether we should go to the right, what we want to do is take the minimum number between P and Q. And if the smallest number between P and Q is greater than the current number we're on, then we know we should discover or we should search in the right subtree. But like I said, the maximum between P and Q is 3. And since the larger number between P and Q is less than 6, let's go to the left. So now we're stuck at 2. 2 is actually the current node itself. And when that's the case, we know that we should just return 2. But let's say 2. So right here, the answer would be 2. We just have to return 2 because once we're on the node 2, we cannot go any deeper because once we go to the left, we only have 0 and we wouldn't have 2 or 3 as its descendants. But let's say that wasn't the case. Let's say P was 5. So now we're on 2. Should we go to the left or to the right? Well, let's say we should go to the left. Let's take the larger number between P and Q, which is 5. If 5 is less than 2, we go to the left. But 5 is greater than 2, so we don't do that. Now let's see if we should go to the right. Let's take the smallest number between P and Q, which is 3. Since 3 is greater than 2, and 3 is the smallest number between P and Q, that means that both P and Q will be on the right subtree of 2. So we move to the right. And now we're looking at 4. Now here at 4, let's see if we should move left or right. The maximum between P and Q is Q. I'm sorry, the maximum is P, which is 5. Is 5 less than 4? 5 is not less than 4. 5 is greater than 4, so we know to not move to the right. To not move to the left. Now let's see if we should move to the right. Let's get the minimum between P and Q, which is 3. Is 3 greater than 4? It is not. Since the larger number, since the smaller number between P and Q is not greater than 4, and the larger number between P and Q is not less than 4, that means that one is going to be on the left subtree and the other is going to be on the right subtree. And when that's the case, we just return 4, which here is the correct answer. So now let's see how this code would look like. So we will want a while loop to iterate over this tree. And the condition we want in this while loop is while our node is not none. Now, while that's the case, let's determine if we should move to the left. We know to move to the left if the maximum between P and Q is less than the current node we're on. So if the maximum between P and Q is less than the current node we're on, then we know that P and Q is both on the left subtree. So let's overwrite node to be equal to node.left. But let's say this doesn't go through. Let's say the maximum between P and Q is greater than the current node we're looking at. If that's the case, let's say we should go to the right. If the minimum between P and Q is greater than the current node we're on, then that means that both P and Q is on the right subtree. So let's overwrite node and let's make it equal to node.right. But if neither of these check out, then that means that one is going to be on the left subtree and the other is going to be on the right subtree. And if that's the case, that means that the current node we're on is the answer. Now keep in mind here, I'm not using equals to. The reason I'm not using that is because if I exclude that, that makes us hit this else block. Whoops. That makes us hit this else block when the lowest common ancestor is either P or Q. So for example, if P was 2 and then Q was 4, the answer will be 2. And that's why I'm not using the equal sign for any of those if or else if. All right, so that's actually all the code we have to write. So now let's see if this is actually right and this is an accepted answer. Okay, let me move this over here. Perfect. So let's create that while loop. Now, let's check if we should move to the left. So if the max between P and Q, if that is less than the current value of the node we're looking at, then that means that we have to move to the left. So let's overwrite root to be equal to root.left. Else, if the minimum between P and Q, if that's greater than the current node we're looking at, then we know that P and Q are going to be on the right hand side, on the right subtree. Else, if P, for example, if P is on the left and Q is on the right, or Q is on the left and P is on the right, then the current node we're looking at is the actual answer, and that's what we want to return. And this is all the code we need. So let's see if this actually works. So it gets accepted here. Now let's submit it. Awesome, and then it gets accepted. Now something I do want to point out is that the time complexity of this algorithm is going to be big O of n. The reason for that is because we might have to explore or we might have to look at every single node in the tree to find the lowest common ancestor. And then the space complexity is constant, because we're not appending to an array or creating a hash map or a hash set. We're just comparing values and using and overwriting variables. So other than that, that's really it. If you guys did enjoy this video, then make sure to subscribe to our YouTube channel and leave a like. And if you guys want to do more problems like these, then make sure to join our Discord channel, which is linked down below. We send out both beginner and advanced problems every single day, just to get people used to these problems and help them become a better programmer for interviews and applications as well, to hopefully get you guys a job. So yeah, other than that, I hope you guys did enjoy the video. Thank you for watching and have a nice day.